we are going to learn how to use the principle of mass induction to prove that this is true. We want to use the principle of mass induction to show that if we sum up this series, it will give us this. Of course, you know that this is okay. Chiadika. Please be patient. If we have 1 squared plus 2 squared plus 3 squared plus dot plus n squared, this is called a series. Why? Why is it called a series? Anybody? Why is it called a series? Anybody? Why is it called a series?
Because
Continuous. It is called a series because we added them up. It's supposed to be a sequence without the addition sign. So with the addition sign, it is called what? A series. So if you have this type of series, this is the formula for you to sum them up. Do you understand? So we want to use the principle of mass induction to prove that this will yield this. So what is the principle of mass induction? The principle of mass induction states that this will be true for all natural numbers. If 1, it is true for s of 1. The principle of mass induction states that this formula will be true for all natural numbers. If 1, it is true for s of 1, and it is true for what? S of k plus 1. Based on the assumption that s of k is true. That's what you have, right?
Yes, sir.
So that's what we are going to use to show this now. So to do that, we are going to start with the first step. Step 1. Step 1, we want to verify for s of 1. We want to verify for s of what?
1.
So what's our s of n? Our s of n is this. S of n is n into n plus 1, 2n plus 1 over 6. This is our s of n. So that means to verify for s of 1, we replace this n with what?
1.
We replace the n with what?
1.
So that is what we're going to do here. But before we will replace, we have a question, success. Question? Okay, before we replace n with 1, let's consider the left-hand side. For the left-hand side, if n is 1, how many terms will you count here?
2.
Eh? You count what? You count 1 term. N is 1. So you count just 1 term. Is that clear?
Yes, sir.
So you count the first term. Success, what is the first term here?
1
Okay, tell me further. 1 squared is the first term here. And 1 squared is what? Is 1. So the left hand side resulted to 1. So we want to check if the right hand side will result to 1 too. So let's check the right hand side. Anywhere you see n, you put what? 1. So we have 1 into 1 plus 1, 2 into 1, everything over 6. So you do the one inside the bracket first. 1 plus 1 is what? 2. 2 times 1 is what? 2 plus 1
3.
over what?
6.
So 1 times 2 times 3. 6 divided by 6.
1.
So we can see that the right hand side gave us 1. So we can conclude that this is true. It is true for s of what? 1. It is true for what?
S of 1.
So that is the first step. Now, what I will do is to check for s of 2. Why do I need to check for s of 2 when it is not stated in the theorem? I will check for s of 2 so that when I'm going to prove for s of k plus 1, I will be sure of what I'm doing. To be certain that this formula is truly correct, I will check for s of what? 2. I will check for s of what?
2.
Okay, Joshua, you have a question.
So what happens if
if s of 1 is not true, then the formula is not even correct. So you stop there that it is not true for all natural numbers. So you stop there. That ends the problem. Do you understand?
Yes, sir.
Okay, now, so if I check for s of 2, if n is 2, okay, how many terms will I count? If n is 2, I will count how many terms? 2 terms. So what are those 2 terms? 1 squared plus what? 2 squared. So 1 squared is what? 2 squared is what? 1 plus 4, 5. So that is for the left hand side. Now let's see if the right hand side will still give us the same 5. So for the right hand side, anywhere you see n, you put what? You put what? You put what? You put what? You put 2, s of 2. So we have 2 into 2 plus 1, 2 times 2 plus 1 over 6. Eh? Said
This step 2 was this step 2.
we have not entered step 2. I said I would like to check for s of 2 to be sure that the formula is correct. So that when I enter step 3, which is s of k plus 1, I can struggle to make it right. So s of 2 will be 2 times what? 3. 2 times 2 is what? 4 plus 1. So we have over 6. 2 times 3 times 5 over 6 is what?
30.
So this we cancel 2 times 3, which is 6. Then you have what? 5. Is that correct?
Yes, sir.
Or you say 30 divided by 6 is what? 5. So the right hand side is 5, the left hand side is 5. That means it is true for s of 2. Are we good now?
Yes, sir.
Now, so let's move to step 2. So what will be our step 2? What will be our step 2?
Step 2, you substitute everywhere that there is n, you put k.
So step 2, you're going to assume that it is true for s of what? K. So we are going to assume that it is true for what?
S of K.
For s of K. That means our n is what?
K.
Our n is what?
K.
So looking at the question now, we have 1 squared plus 2 squared plus 3 squared plus k squared equal to what?
K
bracket k plus 1, 2k plus 1 over 6. So we got this equation what? 1. So this is not just an assumption. We don't have too much work to do. We leave that one here. We move to step what?
3.
We move to step what?
3.
So what is step 3? What are we going to do here? In step 3, we have to verify that it is true for what? S of k plus 1. So we want to verify that it is true for s of k plus what? 1. So for s of k plus 1, we have 1 squared, 2 squared, 3 squared, So instead of n squared, what will I write? Instead of n squared, what will I write? N k plus 1 squared will be equal to, instead of n here, what will I write? K plus 1, then k plus 1 plus 1, 2k plus 1. I'll put it in brackets, that's 2n. So 2k plus 1 plus 1. Everything over what? 6. So I can now simplify this. And at the same time, I can expand this sequence, this series, so that this equation 1 can come in. What is our problem here? Our problem is to make sure that this left hand side will give us the same result as this right hand side. But there's another challenge. How will you sum up dot? It seems not to be possible. So that is why we have to bring in this equation 1 here, so that we can replace anything like this with this. So that means this series can also be written as 1 squared plus 2 squared plus 3 squared plus plus, before we have k plus 1, k has been existing already, Abi?
Yes.
So we can write plus k squared, then plus this one, k plus 1 squared. So it is still the same series. The only thing is that we added this, k squared plus k plus 1 square. So the right hand side will yield k plus 1. K plus 1 plus 1 will give us what? K plus 1 plus 1.
K plus 2.
So that's k plus 2. So if we expand this, what will you
K
get?
plus 2.
2k plus 2 plus 1 will give us.
2k plus 3.
Hello, pay attention. 2k plus 2 plus 1 is what?
2k plus 3.
Great. 2k plus 3
All over 6.
over what? 6. Are we good?
Yes, sir.
Can we continue?
Yes, sir.
Now, you can see that from here to this point is the same thing as what? Equation 1. Right or wrong?
Right.
From here to this point is the same as from here to this point, which is the same thing as this. Huh? Ike, are we together? Are we together, Ike? Talk now. So we can say put equation 1 in 2. Let's call this one equation 2. So we can say put equation 1 in where? In equation 2. So I'm going to replace this guy here with this one. So that will be k into k plus 1, 2k plus 1 over what? 6. I just replaced this. So I'm still going to write this. That will be plus k plus 1 squared over what? 1. So my intention now is to simplify this to make it look like this. So you can see that I don't have my dot 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 again. I've replaced this dot dot dot. Emmanuel, are we together? So what are we going to do here to simplify it?
First, you have to do k plus 1 square.
No, you don't need to expand.
Then your find your lowest multiple.
We
is
find the LCM. So what is the LCM of 6 and 1? What's the LCM of 6 and 1?
6.
What's the LCM of 6 and 1?
6.
So we have 6. 6 divided by 6.
1.
1 times this.
Same.
K plus 1. 2k plus 1. Plus what? K plus 1 squared. Is that correct?
So 6 in 1.
Thank you. So we have 6 divided by 1 is 6. So 6 times this. So 6 times, we're a little bit distracted because of this weather. Enter. So we have that. Right? Now, if we have this, there is something common. Looking at this term and this
K
term,
plus 1.
you see that k plus 1 is what? Common. So you can see the reason why you don't need to expand this.
So that was a square.
You can see the reason why we don't need to expand it. So we can rewrite this as k into k plus 1, 2k plus 1, plus 6 into k plus 1, k plus what? 1 over 6. Squared means multiply it by itself. So that's why we multiply this by k plus 1. So we can now factor out k plus 1. So that if you factor out k plus 1 here, what are we left with? We are left with k into 2k plus what?
1.
Plus, if you factor, so that's 6 into k plus 1. Everything over what? 6. Is that correct? Are we together?
Yes, sir.
Are we together? Blessing, are we together? So I'm going to expand this one inside because there's nothing common in it. So I have k plus 1, 2k squared plus k plus 6k plus 6. Everything over what? 6. So I have k plus 1, 2k squared
Plus 7k.
plus 7k plus 6. Everything over 6. So how will I factorize this? Quadratic factorization. So what are the factors here?
2 and 2
Eh? Sources, what are the factors?
So 3 and 4. 3 and 4.
Sources, what are the factors? Sources, you are not here. So we have k plus 1, we have 3k plus 4k, right?
Yes.
Because 3 times 4 will give us
12.
12, which is 6 times 2. And if you add 3 to 4, you still get this 7k. So we can write this as 2k squared plus 3k plus 4k plus 6. Everything over what? 6. So we have k plus 1 So we can factor out k, that's 2k plus 3. Then we can factor out 2 here. That's 2k plus what? 3. Everything over what? 6. Is that correct? So we have k plus 1. Then look at this. 2k plus 3, 2k plus 3. What will I do? I will factor 1 out. That will be 2k plus what? 3. Then inside I will have what? K plus 2. Everything over 6. So this is what we have. Now compare it to what we have at the right hand side. You can see that this is the same thing as this. We have k plus 1, k plus 1, 2k plus 3, 2k plus 3, k plus 2, k plus 2, 6, 6. So we can conclude that this is the same thing as the what? Right hand side. So since it is the same thing as the right hand side, we can say that this is true. It is true for s of k plus what? 1. Hence, or therefore, it is true for what? For all positive integers. That's what the theorem states. For all positive integers. Any question? Any question? How many of you did that? How many of you did that correctly?